So in the last video, I worked you through the process of going through the row operations to transform the starting matrix into reduced row echelon form. It involves a lot of calculations, but it's the kind of process that if you get enough practice at it, it becomes mechanical and you can just do it without having to really think about it. You have to do lots of calculations, but you don't have to think about what to do next once you get the hang of it and get enough practice at it that it becomes sort of automatic. But of course, the easy thing to do is to just let a calculator or computer or app handle all the gory details and take you directly from the starting matrix to the reduced row echelon form. But you still have to know how to interpret what you end up with. If the calculator gives you the reduced row echelon form, you have to know what to do with that. So now let's talk some more about, once you have the reduced row echelon form, how you would read off the solution to the system from that. Remember that each row of a matrix corresponds to an equation. So you can translate the rows of the matrix back into equations. Remember, the first column is the coefficient on the first variable, the second column is the coefficient on the second variable, and so on until the last column is the constant on the other side of the equal sign. If you have any rows that are just all zeros all the way across, you can ignore those. They're just telling you that 0 times x plus 0 times y plus 0 times z equals 0, and that's going to be true no matter what. But if you have a row that's all zeros except for a number in the last column, like 0, 0, 0, 1, that means there's no solution. You have an inconsistent system, one where there's no way of making all the equations true at the same time. And sometimes when you get to reduced row echelon form, you'll get one or more rows of your matrix that still have more than one variable left. In that case, you have a dependent system with infinitely many solutions, but you still might want to know what those infinitely many solutions are. Infinitely many solutions doesn't mean anything goes. It means there are multiple solutions, but there's usually some pattern that they all have to follow. So to see what the solution set looks like, solve the equation for that first variable. It'll depend on some other variable, and then that other variable could be any real number. So we will see an example or two of that, and hopefully it'll become clearer once you see how that works in an actual example. But let's work through some examples where we go from a matrix to what the solution to the system is. Okay, so here we have the matrix 1, 0, 0, 16, 0, 1, 0, 9, 0, 0, 1, 5. The top row would be telling us that x equals 16. The second row would be telling us that y equals 9. And the third row would be telling us that z equals 5. So the solution to the system would just be 16, 9, 5. Okay, what about this matrix? 1, 0, 11, 0, 1, negative 1, 0, 0, 0. Notice that there are only 2 columns for variables. So this would have been if you started out with a system that had 3 equations, but those 3 equations only involved the 2 variables x and y. So the way it is now, the first equation, or the first row of the matrix, corresponds to the equation 1x plus 0y equals 11. So that's telling you that x has to be 11. And then the second row tells you that 0x plus 1y equals negative 1. So y has to equal negative 1. And there is no z. Those are the only 2 variables, remember? And then the bottom row is just all zeros, so you can ignore that. It's just telling you that 0 times x plus 0 times y equals 0. That's true for these two numbers. It would be true for anything else. So it's not giving you any real information. Now, what about this next example? Now, by the way, this right here is not in reduced row echelon form. But let's say you were trying to solve a system by doing all the row operations yourself. And you were going step by step, and at some point you got to something that looked like this. When you see this, you can just stop right there. Even though it's not in reduced row echelon form yet, I can tell by this bottom row that there is no solution. That's an inconsistent system. Remember, a row that's all zeros except for some other number in the last column means there's no solution, because that would be telling you that 0 times x plus 0 times y plus 0 times z equals 1. And that can't happen. And now this next example here, this is in reduced row echelon form. There's no further I can go with the matrix. But this would be an example of a dependent system. Now the top row of the matrix is telling us that 1 times x plus 0 times y plus 3 times z equals 8. And the middle row of the matrix is telling us that 0 times x plus 1 times y minus 5 times z equals 0. And the bottom row isn't really telling us anything. It's just saying 0x plus 0y plus 0 equals 0. So we can ignore that. But this is an example of where we have a dependent system with infinitely many solutions, but there's a pattern that those infinitely many solutions all have to satisfy. And to see what that is, I'm going to do a little bit of rearranging. So in each equation, I'm going to leave that first variable where it is, but transfer the z term over to the other side. So when I subtract 3z on both sides, that top equation becomes x equals 8 minus 3z. And the second equation, I'm going to add 5z to both sides, and it becomes y equals 5z. So notice how x and y both depend on z. The z can be anything, but then the x and the y that go along with it have to be what it says here. So the solution set is made up of all triples, all x, y, and z, where x is 8 minus 3z, y is 5z, and then z is whatever it is. So here the z can stand for any real number. You can pick any number you want for z, plug it in, and you would get one particular solution. So if you plug in 1, you get 5, 5, 1. You plug in 2, you get 2, 10, 2. Plug in 0, you get 8, 0, 0. Plug in -1, you get 11, -5, -1. And all of those, as well as many others, would be numbers for x, y, and z that would make that system true. Okay, so let's work through some more examples. We have to remember that it's a 3-step process. We have to write the augmented matrix for the system. Then we have to somehow, either by ourselves or with the help of some calculator or app or computer online app or something like that, get the reduced row echelon form of our matrix, and then translate that back into the solution to our system. So for this system, the augmented matrix would be, see if you can tell what it is before I write it down. Okay, so for the first row, the numbers are 1, 1, 1, 1. For the second row, the numbers are 3, -1, -1, 4. And for the third row, the numbers are 1, 5, 5, -1. And I'll just go ahead and do this one on the graphing calculator. So I'm going to enter this matrix into the calculator as matrix A, which is still a 3 by 4 matrix. And so I'm going to put in the numbers 1, 1, 1, 1, 3, -1, -1, 4, 1, 5, 5, -1. And when you've got all the numbers in, don't forget to quit out of that screen before you do anything else. You don't have to do this, but I'm going to look at the matrix I just put in to make sure it looks like it's supposed to look. Yeah, that looks good. And now I'm going to get the reduced row echelon form, the RREF, of the matrix. And it is 1, 0, 0, 0, 0, 1, 1, 0, 0, 0, 0, 1. Notice that bottom row, 0, 0, 0, 1. What does that tell you? No solution. This is an inconsistent system. It has no solution. There's no choice of X, Y, and Z that would satisfy all three of those equations at the same time. How about this next one? This time there's only two equations, but they still involve three variables. So our matrix is going to have two rows, but it's going to have four columns altogether, one for each of the three variables and then one for the constants. So when we put in the numbers, they are 3, 1, 2, -5. And see if you can guess what I'm going to put down here. 1, -2, -4, 10. Okay, let's have the calculator handle the details of getting the reduced row echelon form. I'm going to put in the matrix as matrix A. This time it is a 2 by 4. And the numbers are 3, 1, 2, -5, 1, -2, -4, 10. I'm going to quit out of that. Let's take a quick look at the matrix we just put in to make sure it looks right. Okay. And now let's look at the reduced row echelon form of the matrix. One, 0, 0, 0, 0, 1, 2, -5. Now that 1, 0, 0, 0 is telling me that X has to equal 0. And that 0, 1, 2, -5 is telling me that Y plus 2Z has to equal -5. So this is a dependent system. X has to be 0, and then Y has to equal -5 minus 2Z. So the solution set is 0 for x, -5 minus 2z for y, and then z itself can be anything. So 0, -5 minus 2z, z, where z is any real number.